This little video is going to deal with some of the very basic concepts in electrostatics. Let's start by reminding ourselves of atomic structure, and we're going to consider carbon. You'll know that diamonds and graphite pencils, both of those are made up of different allotropes of carbon. Carbon arranged in different ways. Now, if you have a look on the periodic table, you'll find that carbon has an atomic number of 6 and a mass number of 12. Let's just quickly remind ourselves what that means. Every atom contains protons that are located in the nucleus of the atom. The atomic number of 6 tells us that there are 6 protons in carbon's nucleus. There are also neutrons in the nucleus. And the mass number of 12 tells us the number of protons and neutrons. So if you take 12 and you subtract the 6 protons, it leaves you with 6 neutrons in the nucleus. So the protons and neutrons are bound together by strong atomic forces, and they form the nucleus of the atom. In a neutral atom, the number of protons equals the number of electrons, and you'll know that electrons orbit around the central nucleus. And with 6 protons in a neutral carbon atom, we'll have 6 electrons, and I assume you'll remember that those are arranged in different shells, different orbitals, and the first 2 electrons orbit in the first shell, on the first energy level, and then the other 4 orbit in the second energy level. We're not going to go into too much more detail about the electrons, it's not necessary. The key point here in terms of atomic structure is to recognize that this this atom contains 6 protons and there are 6 electrons, and so the 6 positive charges neutralize the 6 negative charges, and so overall a carbon atom containing 6 protons and 6 electrons is neutral. Let's now go and consider how one charges an object by friction. If we take a glass rod and a silk cloth and we rub them up and down against each other, we will slowly charge both the glass rod and the silk cloth. The glass rod ends up being positive and the silk cloth being negative. Let's try and see if we can work out why. Firstly, let's focus on the glass rod. Before we started, that glass rod is neutral. And so I've indicated that by showing that there are as many positives as negatives in that glass rod. Now remember, each of those positives relates to a proton in a nucleus somewhere, each negative to an electron. I can't draw all of them, but what we're trying to illustrate here is there are equal number of positives and negatives, and hence that glass rod is neutral. The silk cloth similarly has got an equal number of positives and negatives, and hence is neutral. Now, as one rubs the silk cloth up and down against the glass rod, the friction causes a movement of electrons. Now, it's really important that you understand that the protons, the positive charges, are bound in the nucleus. They can't move. So we cannot have a movement of protons from one area to another, but the electrons, particularly the outer shell electrons or the valence electrons, are relatively far away from the nucleus, and we can have a movement of those electrons. So if we focus on one particular electron on the glass rod, as the silk cloth rubs up and down against it, that electron will be transferred from the glass rod over onto the silk cloth. So as we go up and down, you'll see that a number of the electrons on the glass rod have now moved onto the silk cloth. Now, by no means do all the electrons move, obviously. There are a huge number on the glass rod, but we have sufficient electrons moving from the rod onto the silk cloth, such that on the glass rod we now have more positive charges than negative charges, i.e. more protons than electrons, and hence the glass rod becomes positively charged because it's lost some of its electrons. The silk cloth has more electrons than protons, and so it becomes negatively charged because it's gained electrons, and so there are more electrons than protons. And so that's how one charges objects by friction. If we look at charging objects by induction, if you imagine we have a polystyrene sphere suspended by a light string, it starts off as being neutral. Once again, that means there are as many positives as negatives. If we bring a charged object nearby, in this case we've brought a positively charged object close by to this neutral polystyrene sphere, then the electrons in that sphere are attracted to the positive object, and so that electron over there will be attracted over to the left-hand side of the sphere and will move along with the other electrons towards that left side of the sphere. And so we now have a positively charged object, and the sphere, if you look at that, the left-hand side is now negatively charged because there are more electrons. Obviously the positives can't move because they're the protons in the nucleus, but if you have a look at the right-hand side of the sphere, there are more positives and negatives, so the right-hand side has become positive, the left negative. And you remember that positives attract negatives, and so the positive blue object now will be attracted to the polystyrene sphere, and that sphere, if it's suspended by a light string, will move towards the positive object. And that's simple charging by induction. Just consider finally one or two issues to do with calculating charge. Just a reminder that the symbol we use for charge is a Q, and we tend to use a small q if it's a very little charge, and a capital Q if it's a slightly bigger charge. And that charge is measured in coulombs, and coulombs is given, the symbol for that unit is a capital C. Now, obviously the electrons are crucial as we're moving electrons between objects. And an electron carries a fundamental charge, we call it, and that charge is a charge of minus 1.6 times 10 to the minus 19 coulombs. A proton has the same charge as an electron, but obviously it's a positive charge, so its charge is positive 1.6 times 10 to the minus 19 coulombs. 1 coulomb of charge is really a very large charge, and a quick calculation, if we take 1 coulomb of charge divided by the charge of 1 electron, it tells us that we would need 6.25 times 10 to the 18 electrons to make 1 coulomb of charge, and that really is a very large charge indeed. We tend to deal with objects that are given a charge of a certain number of microcoulombs often, and just a reminder that the prefix micro refers to 10 to the minus 6, a millionth of a coulomb, and sometimes even a smaller charge, a nanocoulomb, and there the prefix is 10 to the minus 9 of a coulomb.